So, all right, just to recap, so this is the second lecture. Last time we've talked about review of probability theory. So today we will review linear algebra and review multidimensional calculus. And finally, if we have time, we'll talk about concentration bounds. It's gonna be a systematic study of the concentration bounds. It's a nice transition from our review of prerequisite to the real lectures. Because the first few part of the lectures will be focusing on PAC models and consistent learning and sample complexity. So concentration bounds are going to be very helpful. And concentration bounds are also very closely related to the review of probability theory, linear algebra, multidimensional calculus. So hopefully we'll have time to cover them today, okay? All right. So if there's no further question, let's move on. So first I wanted to do reviews of the linear algebra. Last time we've already talked very briefly about inner products. So today I will focusing on Cauchy-Schwarz inequality, triangle inequality, reverse triangle inequality, vectors, matrix norms, equivalence of LP norms, some basic norm inequalities, which will be very useful for the later proofs. Okay, so, I'm sure everyone is familiar with Cauchy-Schwarz inequality given A, B vectors in the n-dimensional space. The inner product of the A and B, okay? And then the absolute value of the inner product, because the inner product is scalar, it could be a negative value, it could be a 0, it could be a positive value. So you take an absolute value of that, and it is guaranteed that this absolute value is smaller than or equal to the multiplication of the norm A and norm B. Okay, so this is probably most important inequality out there. So can anyone tell me when does this equality hold? I mean, this is an inequality, but under which condition do you think the equality would hold?
When A or B are multiple of each other.
Yeah, they're in the same direction. True. What about, yeah, so they might be in a reverse direction, right? The multiplication could be a negative number as well. Agree? Okay, yeah, so this is used to derive the triangle inequality. So what is a triangle inequality? Given AB, again, in a dimensional space, AB vectors, the norm of the summation of the two is gonna be smaller than the summation of the norm. Okay, so now when does this inequality hold? Any idea?
Also when one is a multiple of the other, right?
Right. What if they are so there are two situations, they're in the same direction versus they're in the reverse direction.
Yeah.
So which do you think, if they are, the opposite direction, would that hold?
Oh, right. Yeah, then it doesn't hold.
Right.
Same direction.
So you see the equality hold for the Cauchy-Schwarz versus for the triangle is actually a little bit different. Right? Mm-hmm. Okay. All right. So then there's a reverse triangle inequality. AB norm, A plus B norm is greater than the subtraction of the two, right? In any direction, A minus B or B, A norm minus B norm or B norm minus A norm. Okay. All right. So what is a norm? Everyone knows what's a norm, but basically a norm assigns a positive number. Well, it could be actually is a non-negative number, okay? But it is a positive number to each non-zero vector. If it is a zero vector, then it will be a 0, okay? So key aspect, improving uniqueness results. This is going to be very important. So there are some norm properties in case people, really need to, for a systematic understanding of the norm, I think it is best to recall some of the very basic properties, but sometimes we not necessarily really are thinking about it once we get really, familiar with norms. Homogeneity, right? So this is saying that if you have a scalar multiplying with the vector, the norm will be equivalent to the absolute value of the scalar multiplied with the vector norm. Okay. Now, subadditivity basically is a triangle inequality. Okay. And separability, if and only if the norm is 0, then the x vector will be 0. Okay. Now, so here are a few examples. Is this L2 norm a norm? L2, you can imagine, is the square root of the summation. So it's the square root of the element squared summation. Right? It is a norm. What about L0 norm? Right? It counts the number of non-zeros. It's also a norm. What is L1 norm? Okay.
Sum of all the absolute values of each an individual entry is the L1 norm.
Right. Oh, someone's saying it's Manhattan norm. What about Manhattan norm? Is it the same as L1 norm?
Yes.
Okay. All right. So what about this one, the gradient of x, norm 2?
Not
Is
a
it
norm.
norm?
Not a norm.
Not a norm? Okay, we'll see later, okay? Because the gradient of x is, depending on what you're taking derivative with respect, right? It could be a matrix. Well, if it's a matrix, what is the L2 norm of a matrix? We'll see. So what about the square root of x transpose ax for some matrix x? So x is being a vector. So x transpose ax is just a scalar. Now take a square root of that. Is this a norm? Yeah, this is indeed also a norm. So we'll also see that.
No, I thought that was not a norm.
Oh, why is that not a norm?
Depends on the eigenvalues of A.
Okay.
So I also had a question about the second one.
Okay.
Would that one, I think that one wouldn't fulfill homogeneity, would it?
Let's see. So the homogeneity is just, the multiplication of the x being, the multiplication of the vector's norm is just the product of the absolute value of the coefficient multiplied with the norm of the vector itself. Would that be hold here?
The last case will be a norm only if A is a positive semi-definite matrix. Otherwise, it can be negative inside the square root.
Exactly.
Oh yeah, that's true.
Okay, so yeah, if the matrix A is semi-positive definite.
The gradient one can also fail separability, right? If x is just a constant.
Can you speak up?
I think that the gradient norm should fail separability, because if x is a constant, then you can get that the norm is 0 even if x is not 0.
Yeah, so I think it's very hard to say here because the gradient of the x is very vaguely defined here. Okay, so we'll see later on when we have like the multi-calculus. But I just wanted, I don't want you to really think maybe, whether this is the norm or not, but I wanted to use this example to kind of motivate you to think what are the norm properties, okay? So what we'll see, I think the definition of the gradient of x is really vague here. Let's see that later. So do we still have a problem whether the L0 is the norm? The second one.
Yeah, so if you take, for instance, lambda equals 2, so 2x doesn't increase the number of non-zeros in the vector, but then the norm is not 2 times the original number of non-zero entries.
Oh yeah, that's actually right.
Can't we consider the gradient of x as a Frobenius norm? I mean, oh no, we can't do that. That's for the matrix.
Okay, so let me get back to this L0 norm. Right, so let me get back to the L0 norm later, okay? We can discuss that offline. All right, so LP norms. For definition of LP norms, basically is defined as P greater than 1, for anything P greater than 1, for any vector A in n-dimensional space. LP norm is defined as the summation of the entries, absolute value of the entry to the power of P, and then the entire summation taken power of 1 over P, right? So L2 norm, so it's when P is 2, L1 norm, P equals to 1, L infinity norm is taking the maximal value of the absolute values. So the Minkowski inequality, basically, it says that for P greater than 1 or smaller than infinity, you still have the triangle inequality. All right, so here are a few norm balls. So for the BL2 norm, so you can see these are like the unit balls of these norms. So these unit balls basically means that if you set the epsilon to be 1, and set the P to be, for instance, this is setting P to be L2, this is setting P to be 1, this is setting P to be infinity, you'll get these norm balls.
I have a question. Does P have to be an integer in defining a norm, or can it be like 1.2 norm?
So I don't think, in the definition, it prevents you from having T being non-integer, but usually people have used integer ones. I think the convention is to use integer P. Okay, that's a very good question.
Yeah,
so
if you do the ball on the previous page and you do like L 1.5, you'll get a ball between those two balls, which is kind of interesting.
between L1 and L2.
Yeah.
Okay, that's a good point. Yeah, so I suspect maybe it is a continuous changing process if you increase the P, in terms of like the norm balls. Probably the figure will continuously change somehow. Okay. So equivalence of norms, given any two norms, LP, LQ, there exists alpha, beta greater than 0, such that for any A in an n-dimensional space, alpha, the Q norm smaller than P norm of A, smaller than beta Q norm of A. Okay, so this is a very important. Like equivalence result. It's gonna be used in a lot of machine learning applications where, for consistency guarantees, there might be guarantees for different norms, So some kind of equivalence between the norms might help you in terms of bounding the differences between these perturbation, norm of the perturbations. Okay, so we'll see some of them later in this lecture. So,
So this
yes, go ahead.
this equation will hold only if P is greater than hold with any value of P and Q.
Only P greater, what did you say? P greater than Q?
Yes. Or, I mean, what should be the relationship between P and Q?
Oh, so for any two norms, it's just P.
Okay, irrespective. Okay.
Yeah, so there exists alpha and beta. So this is for any two norms, there exists alpha and beta. But of course, for different P and Q, the alpha and beta will be different. Okay. All right.
Yeah.
So this is a very important result. L infinity norm is smaller than L2 norm and smaller than square root of n being the dimension, L infinity norm. L infinity norm is also smaller than L1 norm, smaller than n times infinity norm. So I see some discussions about whether P is smaller than 1 even being a norm or not. Right, so Chen Chen is saying here, yeah, I guess, we were talking about like this LP norms, we were essentially really talking about P greater than 1. Okay, greater than equal to 1. So I'll think about like when P is smaller than 1, what are the interpretation of these norms. Okay.
Or I guess P less than 1 is not a norm.
Okay, yeah, I'll have to check that. Yeah, so Carol sent a link to talk about when P is smaller than 1. Says if you wanted to see an image of LP norm from 1 to infinity, the shape will follow such patterns. By definition, no reason you cannot have non-integer LP norms, and that's what Carol was saying regarding to the question about whether P should be integer or not. But he's also says that the link is talking about P smaller than 1. So let's talk about that offline. Okay, we have a lot to talk today, so let's not be too bugged on this. Right? So. Okay, so this equivalence norm basically implies that all LP norms behave in principle very similarly. However, we show that they have their distinct properties. So here is a general equivalence LP norm lemma. It basically says that for P and Q, where so for P smaller than Q, and for both being greater than equal to 1, you have the Q norm smaller than P norm and smaller than n to the power of 1 over P minus 1 over Q norm. Okay, so this is a rather interesting result. All right, so two important inequalities, Holder's inequality. You have the absolute value of the inner product being smaller than P norm, Q norm if PQ are dual norms, right? So the dual norms basically means that 1 over P plus 1 over Q equals to 1. So of course, you also need them to be greater than equal to 1. So PQ are so-called dual norms, right? And generalization of the, basically the generalization of Cauchy-Schwarz inequality, right? So Jensen's inequality, actually, we're going to talk about this in concentration bound as well. We'll talk about how we can prove Jensen's inequality. So if you have a convex function fx with x1, x2 in to be any 2 points in real. So if for any t between the interval from 0 to 1, you have the function. So, what is this part? This f of tx1 plus 1 minus tx2 is just saying you are taking some linear combination, right? So using the coefficient t and 1 minus t for these two dots, right? x1, x2. So basically you have an x1 here, you have an x2 here. You somehow take, the combination, which becomes between x1 and x2. And for that point, the function value of that point is going to be smaller than or equal to the combination of the function values evaluated at x1 and x2. Okay. So this is, I think everyone is familiar with this result. Also, we know that f of summation of ai xi divided by summation of ai. So this is again a linear combination with a normalization, right? So it's a normalized linear combination on these, as many dots as you want. So I could be from 1 to n, and could be any number you choose. So this could be on n such data points. You do a linear combination, kind of normalize it. You get a function value based on this linear combination of the dots. And that function value is going to be smaller than equal to the linear combination of the function values evaluated at these individual points. Right? So this is an extension of this 2-point result to the n-point result. All right, so collection of vectors and subspaces. If you have a set of t vectors, let's say V is a set of A1 through AT, then linear combination of them, if you have coefficients alpha k being in real, then the summation of alpha k ak is a linear combination of these vectors. Okay, so because it is a linear operation you're using here, and the alpha k's are just linear combination coefficients. So linear independence, no vector in V can be written as linear combination of others. That's called linear independence. Okay. So, so what is the span? Span is also very important. We'll be using that a lot. So span of V, is there any? Okay, sorry about that. So that's just my notification. Span of the V is just the collection of X. So what is X? X just being any linear combination. Anything that can be written as a linear combination of these set of vectors A1 through AT. Okay. So that is called the span. Any questions? All right. All right, so now subspace is a collection of vector V in Rn is a subspace if and only if it is closed under linear combinations. Okay, so what does that mean? That means if AB is in this vector space V, then any linear combination of alpha A plus beta B is also in this linear in this V space. So basis of the subspace is the linear independent spanning set. Okay, that is called the basis of the subspace. As long as you find a set that is linear independent, then that's also the spanning set. So it is going to be a basis of the subspace. And dimensionality of this subspace is just the element in the basis. So it is pretty much like, very similar to the concept of rank of a matrix. Any questions so far? Okay. All right, so matrix A, in R m by n, matrix of dimension m by n is just the notation, right? So you can denote it as element Aij. So if usually you will use a caption to denote a matrix, but you're use a smaller case with the with the subscripts indicating the index. So small aij just means the ij's element of the A. But if you put a square bracket on it, this means it's a collection. So it basically hint that you are collecting the ij's for any elements within the matrix A. All right. So you could also write the matrix as, the square bracket of these column vectors, A1 through AN, right? If you write them as row vectors, usually would put a transpose on top of these vectors. So it's going to be A1 transpose. Now, instead of using comma, you might be using semicolon because that's the convention how you usually arrange the row vectors. Okay. So usually if you wanted to set a row by row kind of banner arrangement, you wanted to use semicolon. If it's a column by column, you wanted to use a comma. Okay. All right. So, some of you might not be familiar with this notation, A being square of Aij. This just means the collection of all Ij. All right. So the rank of the matrix is just the largest number of linearly independent columns. And the rank of A is, of course, the same as the rank of A transpose, because it won't change the rank if you do a transpose of a matrix. And it's going to be definitely smaller than equal to the minimum of the 2 dimensions, right? A is in n by n, is an n by n, so it's going to be smaller than the minimum of n. And A is a full rank if rank is equal to the minimum of mn. All right. So, even if A is not a square matrix, it could still be full rank as long as the rank is the same as the minimum of the rows or the columns. Now, matrices are representations of linear operators. This is actually very important. We will see. So, for example, if you think about a neural network, right, you have the input vector. Now your input, let's see a feed-forward neural network with fully connected layers, looking at a fully connected layer. So the neural network can actually, the fully connected layer can be represented as a matrix. So what is this? This is basically a linear operator. You're trying to do a function transformation of these vector into another space using this linear operator. Okay, so this transformation is linear because it is just a matrix. So a matrix A of dimensionality m by n is basically transferring some vector from the n-dimensional space to the m-dimensional space, n being the column and n being the row. Okay, and x, if it is x in an n-dimensional space, then ax is going to be in an m-dimensional space. That is obvious. All right, so matrix norms, vector norms are easier to understand, but matrix norms are advanced versions of vector norms. So definition of spectral norm. Spectral norm is the most commonly used matrix norm. Usually people write it as just, the norm with a subscript 2. But here, we're writing 2, 2, but usually people would just use 2 to, indicate that this is a spectral norm. What is a spectral norm? The spectral norm is basically the maximization of any vector x such that you can the spectral norm is any x such that you can achieve a maximal norm of ax with a normalization of the x, the norm of the x. So what does that mean?
How much a matrix can project a unit vector to a vector of maximum length?
Right. So basically, you can imagine that a linear operation is trying to, kind of project a vector onto another space, right? So is m by n. If A is m by n, you're just trying to project a n-dimensional vector into an m-dimensional vector. So in this n-dimensional space, your vector is actually at the L2 norm is 1. So here, the constraint for. Can you see my cursor?
Yeah.
Okay, awesome. So if the L2 norm of the x is 1, so in the n-dimensional space, you have a vector whose norm is 1. Now, after the linear transformation, what is the norm of the vector in the n-dimensional space. But you're taking the maximum. So for any n-dimensional space with norm 1, if after you do the function transformation of the linear transformation, what is the maximum norm you are able to get? Okay, so that's the interpretation of these spectral norm. And essentially, because of this interpretation, the spectral norm is equivalent to the largest singular value of A. Right? So, of course, AX, spectral norm of AX is going to be smaller than equal to L2 norm of AX is going to be smaller than equal to the spectral norm of A multiplied with the L2 norm of X. So now the question is, when is it equal? For those of you who've already read the slides ahead of time, have you thought about this question? When is it equal? When X is parallel with that maximizing vector. Yeah, David, thank you. Do you agree with David, everyone? Elliot also said when X is an eigenvector.
When X is an eigenvector or parallel to eigenvector.
So let's see. So
it has to be the right eigenvector.
Exactly. So yeah, first let's see, David, do people agree with David? When X is parallel with that maximizing vector, what do you mean by maximizing vector?
From the definition.
Right. True. That is true, but more, I guess that is correct. And Elio said when X is an eigenvector. So my question is, would any eigenvector work? Okay.
No, I think Juan said it, right? It has to be the largest eigenvalue.
True. So Juan actually asked that question saying eigenvector corresponding to largest eigenvalue.
It's the largest absolute value of eigenvalue. Right.
Yes. Okay, awesome. Corresponding to the largest eigenvalue, absolute value, absolute. I guess you should say largest singular value.
Sure.
Okay. All right. So matrix norms. We have the lemma. The spectral norm of A multiplied with B is smaller than the spectral norm of A multiplied with spectral norm of B. So we're not going to show this in class, but it is good exercise for you guys to show it, offline. So induced vector norm, matrix norms. What is the definition of induced one? So before we've talked about spectral norm, right? We're talking about both P and Q being 2. Now, if we make it generalized to any P and Q, then basically, I guess here we also wanted to make sure that the PQs are greater than equal to 1. So then for any P and Q greater than equal to 1, the induced matrix norm is just defined as the maximization of this ratio. Okay, the denominator is the Q norm of AX, and the denominator is the P norm of the X. Okay. So basically, this means that if the LP norm of X is 1 for any LP norm in the n-dimensional space with an LP norm 1 vector, then after you do the linear transformation, you are getting a vector AX, and these vectors, what is the maximal LQ norm of this vector? Okay, so this is the interpretation. Of course, if you set the PQs to be 2, then this is corresponding to the maximal singular value of A. If you set it to be 1, then this is the maximum of the absolute column sums. If you set both PQ to be infinity, it's going to be maximum of the absolute row sums. Okay, so these are some important concepts here. Of course, the most commonly used is PQ being equal to 2. All right.
Sorry, just a quick question. Can A be non-square Or is there anything restricting A to be square in these cases?
No, I don't think A needs to be square.
Okay.
Yeah. So AX Q norm is smaller than PQ norm of A multiplied with P norm of X. This is by definition, right? And also similar to Holder's inequality, you would have the spectral norm of A squared is smaller than equal to the multiplication of 1 norm of A and infinity norm of A. Okay, so that's another interesting result. All right, so other frequently used matrix norms, Frobenius norm. So definition, Frobenius norm of A is just the square of the sum of the absolute values squared. Okay, so actually one interesting thing I wanted to mention is that Frobenius norm is defined for vectors as well, right? It is defined for vectors and defined for matrices. Actually, later on when we learn about tensors, it is also defined for tensors, which is a higher dimensional, multi-dimensional array. It could be, higher dimensional than the matrix. It could be a cube, or it could be a fourth order, or so on. Right? So Frobenius norm, interestingly, is always going to be the absolute value squared of all the entries, summing up and taking the square root, right? So this is always going to be true, no matter whether it's a vector, it's a matrix, tensor. Now, alternative definition of the Frobenius norm for matrix is going to be the trace of A transpose A, and sorry, I forgot to say square root, but also square root the trace of A transpose. And this is rather important for our daily use in many of the machine learning applications. Okay, so go ahead.
So when we say something is defined for a matrix and something is defined for a vector, shouldn't we say like whatever is defined for a matrix, it is inherently defined for a vector as well, because a vector at the end of the day is just a matrix, or a matrix is just a tensor. So whatever is basically...
So actually, when I say matrix, I don't mean a very general sense. I mean, you have a non-zero number of, you have a number of columns and number of rows being greater than equal to 2. So it doesn't mean, a vector is a special case of a matrix. You can think about that as that way, but when I say matrix, I specifically mean that you have more than 2 rows, more than 2 columns.
Okay, makes sense.
Mm-hmm. Okay, so the Frobenius norm is not an induced norm, which is kind of interesting. Now, nuclear norm, which is also something a lot of applications would be, using this concept. It is usually denoted as the star as the subscript of the norm symbol. So it is trace of square root of A transpose A. Right, so what is it? Basically, it's going to be the summation of the singular values. Right? So with sigma I being the singular values of the matrix I, it is the summation of the sigma I. And the nuclear norm is not an induced norm either. Okay, so we've seen 2 special norms other than this induced norm, Frobenius norm and nuclear norm. All matrix norms are also equivalent, and you can refer to VP to see that. So eigenvectors and eigenvalues, this is, a lot of you are already very familiar with this. Just very quickly recap it. First of all, let's consider a special case where A is a square matrix. Then X is an eigenvector and lambda is an eigenvalue of A. Basically, the definition of that basically means that if you do a linear transformation on X, so you do A multiply with X, you get a new vector. The new vector is going to preserve the direction. It is the same direction as the previous vector X. So AX equals to lambda X. Lambda is nothing but a scaling, right? It doesn't change the direction of the vector. So AX is still in the same direction as X. And that is the definition of eigenvector and eigenvalue. All right. So intuition basically is that eigenvectors are vectors in Rn whose direction is preserved under action of A. You know, by action of A, we mean the linear operation, right? So length may change, of course. And eigendecomposition then becomes U d U inverse. So don't confuse this with single value decomposition. Single value decomposition is not U d U inverse, right? It is U d V transpose, whereas U v are unitary matrices. Here, this is U d U inverse. I see a lot of people, you know, mix the two, right? So when you say eigendecomposition, it means, you know, the left and the right factors have to be U and U inverse.
Does it depend if you're looking at the left eigenvector or the right eigenvector?
Okay, yeah. I mean, there is no left and right here, right? I mean, there is, but they're the same. It's U and U inverse. Do you see that?
You're saying the left eigenvector equals the right eigenvector?
No, it's not. So, you know, the left is U and the right is U inverse. They're not equal, but they are related.
No, I just mean there's a different definition of eigenvector for the left eigenvector. And
those are singular value decomposition. That's why we got confused, right? So when we have U sigma V transpose, we have U and V, then those could be different, the left and the right. Those are single value decompositions, okay? We'll see that. But I mean here, for eigendecomposition, it has to be U and U inverse. U doesn't have to be unitary. Okay?
Well, I think for a square matrix, the right and left eigenvectors are same.
By definition, they are the same. Yeah, they are the U. That's what I mean. It has to be U d U inverse. Okay, so it has to be that form. You cannot have U d V inverse, for example, right? And it doesn't require U to be unitary. All right, the spectral theory, if A equals to A Hermitian, then the matrix is symmetric, right? All eigenvalues are real, and eigenvectors are of its different eigenvalues are perpendicular, orthogonal. There exists a complete orthogonal basis of eigenvectors. Okay, so basically, you know, if A is not necessarily having this property of A equals to A Hermitian, then going back to the eigendecomposition, you don't know what's the property of the U. Okay? So here, I'm talking about this U here. But now when A equals to A Hermitian, then you know this matrix is symmetric and all eigenvalues are going to be real. And the eigenvectors with different eigenvalues are going to be orthogonal. Yeah, so that's true. H is Hermitian conjugate. Yes. Yeah. That thanks, David. Thanks, Chen Chen. All right. So, any questions before we go to single value decomposition? I think there is a confusion between eigenvalue decomposition and single value decomposition. All right. So let's go to singular value decomposition. We'll review eigendecomposition when we go through. So here you can see A is written, A doesn't have to be a square matrix anymore, right? So here eigendecomposition is for a square matrix. Do you see that? N by N. Now here, the singular value decomposition, you have N by N matrix written as U sigma V transpose. So U and V are unitary. It is very important to know that U and V are unitary. And of course, sigma is diagonal, right? It is a, it's a diagonal, but it's not necessarily squared. So you would imagine that you are chopping off some part of a square matrix, a square diagonal matrix, right? If M is greater than N, then you're chopping off some columns. If M is smaller than N, you're chopping off some rows. Okay, so are we still discussing about the Hermitian transpose or Hermitian conjugate, or very good?
Oh, we were just defined. I just defined it. I think it's probably fine.
Okay. Oh, okay. Thank you, Joshua. Awesome. All right. So SVD, all right, definition, you can see the difference between SV and eigendecomposition, right? So first difference is that the matrix doesn't have to be squared for SVD, right? It could be n by n. Second, you don't require this, the decomposition is also different. Eigendecomposition is U sigma U inverse. Here, the singular value decomposition is U sigma V transpose, but the U and V's have to be unitary. Whereas in eigendecompositions, those U's don't have to be unitary. Okay, but of course, if it's symmetric, then it's gonna be unitary. Okay, so if the A matrix is symmetric for the squared A matrix, then the eigendecomposition will have unitary basis. Whereas singular value decomposition, you have to find a unitary basis. But if you wanted to find a unitary basis, then you cannot always guarantee you can find that. Like your left and the right singular vectors are not necessarily equal. Okay? So you can see the difference between the two. Yes, true. So, because A is real, so this Hermitian becomes transpose. Yeah, thanks David for explaining that. Okay, so someone is asking T transpose should actually be, V transpose should actually be V Hermitian, but because it's real, so it's just transpose. So diagonal entries sigma are called the singular values, and they are positive in real. Typically, you can order them in a descending order. So it's going to be sigma 1 greater than or equal to sigma 2, and so on until sigma r, if the rank is r. So singular values are the eigenvalues of square root of A transpose A and square root of AA transpose. So can someone tell me why? So first of all, if you have a matrix A, which is n by n, what is the dimensionality of A transpose A? N by n, right? So it is gonna be a square matrix, okay? And then, you know that for square matrix, eigendecomposition is defined. Also, if it's A transpose A, it's gonna be symmetric. The question is A transpose A symmetric?
Yes, always.
Yeah, and AA transpose is also symmetric, right? It is gonna be n by n, but it's also symmetric. So now you're basically having a square matrix with symmetric entries. So what is the property here? You'll always have a complete orthogonal basis of eigenvectors. Okay. So that's why singular values actually becomes the eigenvalues of the square root of A transpose A and square root of A transpose. Okay, so if A equals to A transpose, then singular values are the same as the eigenvalues. And that's why, a lot of us are very confused and, kind of mix singular value decomposition and eigendecomposition. Because we're always considering, when we're first learning these concepts, we're always considering this special case of A equals to A transpose. Okay? All right, so the ratio of the largest and smallest singular value is the condition number, and this is very important as well. Right, so remember, condition number is not defined on eigendecomposition, it's defined on singular value decomposition, and it's the ratio of the largest and to the smallest singular value. It's also worth noting that the singular values are always positive. Okay. Oh, as long as the A is a real, right? All right. Now, you know, a lot of us are familiar with the solving linear equation, like a least squares problem, right? A lot of you call it least squares problem. Let's say A is a square matrix. Then, you know, let's see the scenarios if A is full rank and M equals to N, so it's a square matrix. Then this implies that this kind of implies A inverse exists because it's, you know, full rank, right? So given Y, the unique solution X can be estimated as the inverse of the A multiplied with Y. So what is this basically saying? They're saying that you're kind of estimating X based on Y and A, right? So you're basically like solving a least squares problem. All right. All right, so that is the review of the linear algebra. Now, I think another very important, you know, set of concepts are multidimensional calculus. Of course, calculus, everyone's learned calculus, and classically, calculus is just study of the relationship between variables and the rates of change, right? So especially we will be concerned about the gradient, I guess derivative here. However, this is not what we use calculus for in machine learning. We use differential calculus as a method of finding extremes of functions, and we use integral calculus as a method for probabilistic modeling. So we will see when we, you know, we will be learning a little bit about, you know, probabilistic modeling later on. And we'll see a lot of integrals and marginalizations actually, because we will be focusing on some discrete random variables. You know, if we do Gaussians, of course, we'll have to use integrals as well. So differential calculus is very useful for finding extremes of functions. So you can think about convex optimization, non-convex optimization, especially, you know, now we're working on neural nets a lot. So mostly focusing on non-convex optimization. So differential calculus, especially multi-dimensional differential calculus, is very important. So what is differential calculus? Very quickly recap it. A derivative of a function at a point is the slope of the function at that point, right? Very intuitive and geometrically clear. The derivative of f with respect to x denoted as, you know, partial f divided by partial x is often sometimes we use f prime x 0, but I don't like this notation because this doesn't tell you what you are taking derivative with respect to, right? So this is a derivative of f, that's fine, but what are you taking this derivative with respect to is unclear. So I like this notation better, which is the, you know, partial f divided by partial x. So this is clear. You're taking derivative of f with respect to x. And you're evaluating this quantity at x equals to x0. So this is even more clear, right? Now, of course, this is kind of clear because this is basically saying that you're taking, you're evaluating, because the notation usually, you're saying x0. So you would, you know, basically this implies that you're taking a value at x where x is x0, right? But if you're not using the notation, let's say I'm using a here, so f prime of a, so it is probably hard for you to guess what are you taking you know, gradient with respect to. So when I'm reading, when we are reading a lot of like deep learning papers, I think it is sometimes unclear as in what derivatives they're taking. So I hope, you know, after you guys take this course, you will be more cautious, precise in denoting these things, right? So this derivative, again, you know, everyone knows this definition, is taking the limit of h, sorry, this is typo, h going to 0. So it's f of x0 plus the h, very small perturbation, minus this fx0. and divided by the perturbation. Right? So this is a scalar scenario. The x is in a scalar space. F is also in a scalar space. And that's how we first learned differential calculus. Of course, there are a lot of things you wanted to remember, but I don't think we need to go through this together. Now, this multidimensional equivalence of the derivatives is more important to what we wanted to say. So suppose we have vectors w and x in a function of f of wx. So w is a vector, x is a vector, but f is a scalar. So what does this remind you? Of course, this w transpose x is very simple, but if you consider it as a composition of nonlinear functions, then this could be a neural network. W could be the parameters, x could be the input, and f could be your output of the neural net, right? So we might want to differentiate f with respect to w so that we can minimize f. Again, this is a typo. I plan to bold it because it's a vector w. Sorry about that. So this is differentiate with respect to vectors. Okay. So again, let's make the notations clear. F w has entries w1 through wd. So it's in d-dimensional space. You have d parameters in your neural network, let's say. But your neural network somehow is a very simple one. Let's say it's an inner product between the input and the parameters. So fw, again, is in real, right? We compute the partial derivative of f with respect to each component of w. So you can imagine w has all the parameters, and each component of w is each weight in your neural net, right? So now you take the partial derivative with respect to each component of the w. So what is each of these? Each of these are just a univariate derivative, right? So which you can go back to your differential calculus to calculate these. Now, if you package them together into a vector, then what you will get is so-called the gradient. It's just a fancy way of saying this collection of derivatives, right? So it's called a gradient. The gradient is a vector. If you're taking, a gradient with respect to a vector, if you're taking gradient of a function, of a scalar function with respect to a vector, it's gonna be a vector. Okay. So for instance, here, if you package all the univariate derivatives with respect to each component of w as a vector, then this becomes the gradient. The gradient is a function, and it's basically is like a velocity each available direction. All right. So multidimensional equivalence of second derivatives. Again, as you can imagine, if I use H as this, Hermitian of the matrix, Hermitian matrix, sorry, not Hermitian of the matrix, I mean Hermitian matrix, then you are just packaging, the second derivative of a function into a matrix. Now, imagine you have two directions, right? So you're taking the first direction at W1, and then the second direction again at W1. But now for this entry, you're taking first direction at W1, the second was W2, right? So the Hessian is basically the function, it basically means the rate at which different dimensions accelerate together. So, for example, if let's say H sub 2, 2 is high. So what is sub 2, 2? Basically, it's this entry. So if it is high, then it means that there is a high positive rate of changing in the second direction. In the second dimension. Okay, and the dimension is denoted by W1, W2, WD. So for instance, if H of let's say 1, 2 here, let's say H of 1, 2 is high, then basically it means that as we accelerate in the first dimension, we simultaneously accelerate in the second dimension. Does that make sense?
No, that doesn't really make sense to me.
What's the question?
So on the diagonal, you have the accelerations in each dimension, right?
Mm-hmm.
But then off diagonal, how am I supposed to visualize this? Let's say, assume the diagonal was 0, and then off diagonal is non-zero. Then how would I visualize accelerating in the pair of dimensions in that case?
Yeah, is it possible? So yeah, I mean, if your diagonal is 0, then it is unlikely that the off diagonal will be non-zero, right?
It can be non-zero. If, for example, the function f of x,
Mhm.
y equals xy.
Okay. Fxy equals to xy.
Yeah, f of x comma y equals x times y.
Okay. So right, so I think, what I'm thinking about this, for example, if this thing is high, I think, both will be related. The off diagonal is definitely related to the diagonal, right? Although the relationship is a little bit tricky to, describe. But if you think about this entry here, this is H12. So it's basically, derivative with respect to W1 and with respect to W2. Basically, what this is saying is if it's high, then it means that we kind of accelerate in the first dimension as well as in the second dimension.
Well, in the function that I gave, there's no acceleration in x or y.
Right.
But there is a positive number off diagonal. The xy derivative is 1.
Right. So that basically, I guess that doesn't mean it's acceleration, right? Because you're taking like a first order derivative with respect to the first dimension and with respect to the second dimension.
Okay, I see. Yeah, it's not acceleration. Okay.
Yeah. But it's, it's kind of like the synergy. It's hard to describe. I think we might, another option is we might visualize a heat map of the Hessian. Maybe we can do that offline.
Okay, thanks.
Yeah. Okay. So another thing I wanted to mention to everyone is this matrix cookbook. So, we are talking about this multidimensional equivalence of first order derivative and second order derivative, but there are other, calculus or, probability theory with respect to matrices. Right? So since we've learned a lot of these in vectors or in scalars, I think it is worth to take a look at the matrix cookbook to get an idea of how those extend to matrices if you're not already familiar with those. Okay, so here is a link. So integral calculus is the opposite of a derivative, commonly used for computing areas under a curve, right? So for example, taking expectation is often, you use a lot, you use the integral calculus a lot. It is, you can think of it as a continuous analogous of simple sums. In fact, a lot of us are, kind of interpreting integral as that, as an, continuous analogous of simple sums. And the interpretation of integral as a sum basically is like, suppose we were to discretize the range AB into R many units of width, right? So each width is gonna be A minus B divided by R, right? So you're just dividing them into their very small ranges. Now, we could approximate the area under the curve by a sum over all these units, right? So you can imagine you can do that. Of course, if you have, the R being infinity, then you will get a better and better approximation. But of course, you will induce some error when your R is finite or small. So evaluating fx at each position you can do that, right? And then you can multiply by the weight, by the width. So that's gonna be like the approximation of the area under the curve. Right? However, if your R goes to infinity, then the width of each rectangle will approach 0. And we name this width dx. And that therefore the integral notation basically mimics almost exactly as the rectangular sum notation. So that's the interpretation of the integral as a sum. Actually, what does this remind you? Have people, thought about these kernels? Sometimes you can also interpret kernels as some approximation using like this very, like a rectangle also interpretation. But, maybe you're not, if you haven't learned about this, that's fine. We don't have to talk about it online today. All right. So basically, that's what I wanted to talk about, for like a review of the prerequisite for this course. So any comments? So I'll get back to the norm definition. Actually, I apologize that I've never thought about that problem before, about like norm of, a vector when p is, norm p of the vector when p is smaller than 1. So I'll get back, I'll, send a note on Piazza and clarify a few things. But other than that, are there any other questions before we provide a very gentle introduction of these concentration bounds? I won't be going into the details today. Unfortunately, we don't have much time left. But I wanted to, give you a outline, and we can continue that next time.
I had another question.
Sure.
So if you take the derivative of the Hessian, what do you get?
You will get a third order, so you will get a tensor. That's a very good question. So if you have of course, we're talking about multidimensional calculus, right? So you have a function f, right? The function f is a scalar. Now you have the function, you're taking derivative with respect to a vector in Rd dimensional space. So if you take the gradient, it's gonna be a vector of Rd. If you take the Hessian, it's gonna be second order derivative. It's gonna be d by d matrix, Hessian matrix. If you take the gradient of the Hessian, it's gonna be a d by d by d tensor, a cube, if you are not familiar with tensors.
So yes, I'm a little bit confused. I'm familiar with the Hessian as like a bilinear form, like a tensor just as a bilinear form, or
it's a multilinear form. So instead of bilinear, it could be trilinear, it could be multilinear.
Right, and that's what you're saying about the third derivative is a multilinear form with the 3.
Yeah.
Okay, is it an alternating multilinear form?
So you could imagine, right? So the tensor would be like, for this, so you would have a few slices of the tensor. So imagine you slice the tensor into matrices, okay?
Yeah.
So each of them is gonna, so let's say this is the first slice of that tensor. So it's gonna be partial 3 power 3f, partial w1 power 3. That's gonna be the first entry. So the 1, 1, 1's entry. But for the ijk's entry, it's gonna be partial f of power 3 divided by partial, wi, partial wj, and partial wk.
So how do you multiply a vector with this cube?
You don't multiply a vector with the cube. What do you mean?
How do you use this three-dimensional cube, this third derivative?
Yeah, so now you're very curious about tensors, and indeed we'll learn about tensor operations in the class.
Okay, great, thanks.
Great motivation though. Okay, any other questions?
I just have a comment. I think it makes sense if we multiply a cube with a vector, we will get a matrix.
Yeah,
Because-
that's true. Actually, it's called contraction. You can contract a, cube with a vector. You can contract a cube with a matrix. You can contract a cube with a cube. Yeah, all these definitions are, all these operations are defined, but it has a subtle definition there. Okay, awesome.
I have a quick question. So for SVD, should we? I haven't done it manually in years. So is that something that we need to remember how to do, or is it enough to understand what we're getting and the concept?
What do you mean learn how to do? You mean like if I give you a matrix, you should be able to give me the SVD of the matrix?
Yeah.
No, we have computers. That's what computers will do for us.
Okay. That's
But
good to know.
it's
Thank you.
important for you to understand the concepts, right? Understand the difference between the eigen decomposition and the singular value decomposition. Understand under which conditions these two are equivalent. Understand the relationship between singular values and eigenvalues.
Okay, thanks.
Sure. Yeah, anything that can be done trivially by a computer is not something I'll test you guys for quiz, for whatever, for exams, we don't have exams, but for homeworks, let's say. Well, I mean, if I'm gonna test that, you're going to use a laptop, or you're using a program to compute it. Okay. Anything else?
When you mentioned the least squares thing,
Okay.
when the matrix is full rank, that is an exact solution.
Mm-hmm.
It's like when you don't have an inverse of it, but you have to.
Meter was pseudo inverse. If you have a matrix, of okay, sorry, this is the Amber emergency alert. Everyone's getting that? Okay, sorry about that. So let's say you have a rectangular matrix m by n. You cannot, basically you cannot have an exact inverse here, right? It has to be a pseudo inverse. Also, if okay, so this is the end, but let's finish this discussion. So it is worthwhile for you to recall the definition of the pseudo inverse. Then the least squares problem would be just x hat being the pseudo inverse of a multiplied with y. But of course, you're right, there will be an error.
Right, I was just specifying that you only need an approximation when you don't have a exact inverse.
True. Actually, I take it back. If your y is exactly ax, right? Then if you take the pseudo inverse of a, I don't think there is an error. Maybe I could be wrong, but I think very likely it won't induce the error. But the thing is, usually what you have is y is approximately ax, and you're getting a noisy observation of y or a.
Yeah.
So usually you would use this, or you would induce an error. Even using the pseudo inverse. Does that answer your question?
Yeah. I was just
okay.
remembering doing
I'm
this
gonna
kind of stuff.
stop recording now.